Propositional satisfiability, or SAT, is the problem of determining whether a set of propositional sentences is satisfiable. Many logic problems can be recast as SAT problems. For example, earlier in the course, we saw that the logical entailment problem in propositional logic can be reduced or recast as a satisfiability problem in propositional logic. People have developed special purpose programs to solve these SAT problems. They're called SAT solvers. These SAT solvers are used in hardware design, software analysis, planning, mathematics, and many other areas. In this section, we will give a brief overview of SAT solving. Methods in SAT solving can be broadly categorized into two categories. They're the complete methods that are guaranteed to give you the correct answer. And then there are incomplete methods. These methods will give you the correct answer when they can, but may also fail to give you an answer. Let's look at a concrete example. Here we have the set of sentences phi, and the question is to determine whether phi is satisfiable. That is, does there exist a truth assignment that satisfies every sentence in phi? Now, in this whole section, we will assume that each sentence is written as a disjunction of atoms or negated atoms. We know that this is okay because every sentence in propositional logic can be rewritten as an equivalent sentence in this form. First, let's look at a truth table method. We should all be familiar with this method from all the way back in week 2 of the course. On the left-hand side, we have the first 3 columns giving us all the different truth assignments on P, Q, and R. Then we look at which of the sentences in phi evaluate to true and which to false. So if we look at the first row here, in the truth assignment assigning false to P, Q, and R, we see that P or Q is false, P or not Q is true, not P or Q is true, not P or not Q or not R is true, and finally, not P or R is false. And because some of the sentences in phi evaluate to false, we know that phi as a whole is not satisfied by this truth assignment. If we examine all the rows, we find that in every row there is at least one sentence in phi that evaluates to false. So we conclude that phi is not satisfied by any truth assignment. That is, it's unsatisfiable. The truth table method is complete because we examine every single truth assignment. It is also impractical, except for very small examples. In the example we just looked at, we had 3 propositions. And we need to examine 2 to the 3rd power, or 8, in number of truth assignments. That's very small. We did it by hand. If you had 10 propositions, you need to examine 1,000 truth assignments. That's still very small for a computer. But because the number of truth assignments grows exponentially in terms of the number of propositions, this quickly gets out of control. By the time you get to 40 propositions, there are about 1 trillion truth assignments to examine. So we need a better methods for larger problems. Observe here that sometimes we don't need to look at a complete truth assignment before we determine that phi is not satisfied. For example, if we look at an incomplete assignment here with P being true, Q being false, and R unknown, we can already tell that the sentence not P or Q is false and that phi is not satisfied. So because we already know this from a partial assignment on P or Q, we don't actually need to go through the work of examining the 2 complete assignments to determine that in each complete assignment, phi is not satisfied. So let's consider searching partial assignments instead of only complete assignments. One way to do that is to use a tree like the one on the screen. We start at the top, at the empty assignment where nothing is known. Then we make choices. For example, if we choose P to be false, we arrive at another partial assignment. And as we continue to make choices, we arrive at the bottom of the tree with the complete assignments. Now, at each partial assignment, we can evaluate whether the set of sentences phi is already falsified. For example, if at this partial assignment we find that phi is already falsified, we don't need to search all the assignments in the subtree below it, because we know that all those assignments would also falsify phi. In this particular case, we only save ourselves from searching 2 more assignments. But in general, when you have a greater number of propositions, this can be a huge subtree that we're pruning away from our search space. This idea gives rise to the basic backtracking search. I'll walk through a concrete example. We have in the blue box the set of sentences phi, and we start searching. First, we choose P to be false, and in this partial assignment, we cannot determine whether phi is satisfied. Next, we continue to make choices, choosing Q to be false. And under this partial assignment, we can already tell that one of the sentences in phi is falsified. So we label this node with an X, and we don't have to search any further under this branch. We backtrack to the most recent decision point and choose a different path. Let's say we choose Q to be true. Now, under this partial assignment, we find that another sentence in phi is falsified. So again, we don't need to search any further down this branch. Again, we backtrack to the most recent decision point where we could have made a different choice. We go all the way back to the empty assignment, and this time we choose P to be true. So far, we cannot determine whether phi is satisfied. So we continue making choices. Choosing Q to be false, we arrive at a partial assignment where we see that phi is falsified because one of the sentences is falsified. Backtracking again, we make a different choice of Q being true. Here, we cannot determine whether phi is satisfied, so we continue making choices. Searching the branch of R being false, we get to a truth assignment where phi is falsified. Backtracking again and making a different choice, we see again that phi is falsified. Now that we have closed off every branch of the search tree with an assignment that falsifies phi, we can conclude that there does not exist any truth assignment that satisfies phi. Again, we reach the same conclusion that phi is unsatisfiable. Comparing the tree we just explored to the full search tree, we see that we've been able to eliminate or prune away the need to search all these subtrees. And again, in this particular example, it's not a huge saving. But in a larger example, where we have more propositional variables, these could be huge subtrees we're pruning away. Let's look at a further optimization that can save us work. For example, when we're given a partial assignment, say P being true, Q and R unknown, we can simplify the set of formulas we're dealing with. A formula that's already satisfied, say P or Q, can be simply tossed away and ignored. A formula that contains a disjunct contradicted by the partial truth assignment can be eliminated. arriving at a simpler formula. Let's look at an example. We have the same set of formulas phi, and let's say we're exploring this node right here, partial assignment with p being true and others unknown. We can already simplify the set of formulas. The first two sentences can be ignored because we see that they're already satisfied. In the next three sentences, we can eliminate the disjunct saying p is false because it's contradicted by the current truth assignment. And we end up with a much simpler set of formulas we're dealing with right here. Being able to simplify the set of formulas is very nice, but it gives us something even more. Notice here that we end up with the formula Q without any other disjuncts. We call this a unit. And we know that the only way to satisfy the unit is to set Q to true. So from this partial assignment right here, we know to explore the branch Q being true while ignoring this whole other subtree involving Q being false. This can give us a major savings. Let's look at the same example we went through earlier, but this time with unit propagation and simplification. We start as before, choosing p to be false. And in blue box, we simplify using this partial assignment. We end up with the simplified set of sentences. We find that we have some units. Choosing one arbitrarily, we search accordingly. In this case, setting Q to be false. We simplify again, and we find that the set of sentences is falsified. Now we backtrack. Previously, we backtracked to this decision point right here, but because we use unit propagation right there, we don't have another decision to make. So we backtrack to the previous decision point where we still had a choice to make, all the way at the top in this case. So choosing p to be true, we simplify again. We find a couple units, and choosing one arbitrarily, we apply unit propagation, fix Q to be true, get to a new partial assignment, and we simplify again. We obtain some more units, and again choosing one to apply unit propagation. We fix R to be false. We determine that the set of sentences is falsified by this assignment. And now we've closed off every branch in the tree, determining again that phi is unsatisfiable. Compared with the search tree we went through using the basic backtracking search, simplification and unit propagation eliminated the need to explore all these subtrees that are grayed out in this picture. If we do the basic backtracking search with the unit propagation optimization we discussed and another optimization called pure literal elimination, we end up with what's essentially the classic DPLL method. This is a very important method because most modern complete SAT solvers are based on some variation of DPLL with many more optimizations than we've discussed. And these SAT solvers are capable of solving large SAT problems. Some SAT problems are still impractical for complete SAT solvers. For example, some instances offer very little opportunity for early pruning. In these cases, one must consider methods that are incomplete. For example, an incomplete search. The basic idea here is to sample a subset of the truth assignments rather than exhausting them. And if in the sample you find a satisfying truth assignment, then you know that the set of sentences is satisfiable. But if you don't find a satisfiable truth assignment, the best you can conclude is that I don't know whether the set of sentences is satisfiable. There might be one satisfying assignment out there, but I haven't found it. We will not look at the details here, but I do encourage you to take a look at the incomplete search methods. Some takeaways. Decades of intense research and engineering has gone into crafting SAT solvers. And as a result, we now have modern SAT solvers that are capable of solving fairly large problems very efficiently. And active research continues in this area. Today, SAT solvers are used to solve many practical problems, and it is definitely a tool to consider when you need to automate problem solving.